share a picture of my daughter. So she's 7.5 months now. So she's actually wearing earmuffs here because I was making some noise in the house. So those are earmuffs. And then here's a picture of her receiving. So it's hard to tell the scale of things, but basically she feels huge now compared to when she was first born. So yeah. So some of you that I know more closely, I sent an announcement about that. So okay, let me go back to. All right. Can you guys see my notebook looking page?
Yes.
Okay, great. Yeah, so I'll be talking about search on the complete graph using something called a lackadaisical quantum walk. So this is actually relates very closely to something that I believe Harmony would have gone over with you guys, which is search on the complete graph where you have one loop, one self loop at each vertex. So I actually want to spend some time, maybe 10 minutes, reviewing that. And we're actually going to practice coding it and programming it to simulate it as well, because I thought that would be fun. And then we'll see how to modify that. So just as a simple example, let's look at K4 because I don't want to draw a graph that's any bigger. So you have a complete graph with 4 vertices. You've got something like this. I'll go ahead and label the vertices 0, 1, 2, and 3. And what you did with Harmony is that every vertex, also had a self loop. And so a quantum walk on this is going to have uh, different amplitudes on these edges or these arcs. And so there would be some amplitude of the particle at vertex 0 pointing at vertex 1. So there'll be some amplitude of that little arrow. There'll be some amplitude of the particle being at vertex 0 pointing at vertex 2, pointing at vertex 3, and also pointing towards itself. And similarly, if the particle is at vertex 1, it can point to vertex 2, 0, 2, 3, or itself. If it's at vertex 2, it can point to 0, 1, 2, or 3. If it's a vertex 3, it can point to the 3 other vertices or itself. So if you look at all these blue arrows, there's a total of 20 different um, uh, different different amplitudes. And so in general, we're going to have to keep track of 20 complex numbers, perhaps. In this case, we'll keep everything real, but basically we're going to keep track of 20 different numbers. And so with these search algorithms, we generally start in a uniform superposition over all the vertices, or sorry, over all of these states. So the idea is the initial state, which I'll call, let's switch back to a black pen. So the initial state, which I'll call psi at time 0, if it's going to be a uniform superposition over all 20 of these, it's going to be each amplitude is going to be 1 over the square root of 20. So the amplitude of, say, 0 pointing to itself, which I'll denote as 0, 0. So this is vertex 0 pointing to vertex 0. Plus we have 1 over the square root of 20 of being at vertex 0 pointing to vertex 1, all the way through 1 over the square root of 20. I guess the last one would be vertex 3 pointing to itself. So the idea is that we have the same amplitude initially for all of these different amplitudes. So all of them are 1 over the square root of 20. So this will be our initial state. And the way the search algorithm works is we're going to repeatedly apply some unitary operator, which is going to be an oracle query, a coin flip that will shuffle the amplitudes at each vertex, and then a shift or a jump between neighboring vertices. In this case, they're all neighboring each other. And so let's go ahead and break down each of these. So the oracle query, what it does is it flips the sign of the amplitudes at the marked vertex. So let's pick a marked vertex. So without loss of generalization, we'll just pick this 0 vertex to be the marked one, and so the other ones are unmarked. So what this oracle query will do is it will flip the signs of all of these. So all of these that started off as 1 over the square root of 20, they will become negative 1 over the square root of 20, negative 1 over the square root of 20, negative 1 over the square root of 20, negative 1 over the square root of 20. And all of these other ones will remain unchanged. So these remain positive 1 over the square root of 20. So the state after that is going to be negative 1 over the square root of 20 for 0 pointing to itself, 0 pointing to 1. I'm going to factor out this. 0 pointing to 1, 0 pointing to 2, and 0 pointing to 3. And the amplitude will remain positive 1 over the square root of 20 for all the other ones. So you'll have vertex 1 pointing to vertex 0 through all of these remaining 16 amplitudes. So I think vertex 3 pointing to itself would be the last one in order if we put it in numerical order. Okay. So that's the first part of this one step. The next part is the coin flip, which is typically the Grover coin. And what that does is it inverts each amplitude around the average amplitude at that vertex. And then it'll do the same thing here. It'll invert each of these amplitudes around the average amplitude at that vertex, and the same thing here, and the same thing here. And so this first step actually isn't too interesting. So remember, all of these amplitudes after this query, all of these amplitudes are minus 1 over the square root of 20, which means the average of them is exactly that. It's minus 1 over the square root of 20. So let me write this down. So let's say at vertex 1, the average, which I'll write as mu, for like a mean or an average, is just going to be literally minus 1 over the square root of 20 plus minus 1 over the square root of 20 plus minus 1 over the square root of 20 plus minus 1 over the square root of 20 divided by 4. I'm just calculating the average, which of course is minus 1 over the square root of 20. And now if I reflect each of these amplitudes of minus 1 over the square root of 20 about this average, nothing happens. What I mean by reflect or invert is if I draw a number line, like a real number line, and let's say here is minus 1 over the square root of 20. If the amplitude was here, what would happen is it would end up the same distance on the other side. It would end up over here, and vice versa. So that's what I mean by invert. In this case, each amplitude is at the average, so nothing's going to happen. So it's not very interesting in this first step, but as you take more steps, more interesting behaviors happen. So in this case, nothing happens after this coin. So nothing happens at this vertex because all of these vertices are equal to their average. And we're going to have the same story at these other vertices as well. So here, all the amplitudes are positive 1 over the square root of 20. So if you average these 4 vertices, the average is still positive 1 over the square root of 20. So if you invert all of these about that average, nothing happens. And the same thing here and the same thing here. So actually, the state of the system after the coin, so we have our initial state, we've applied the query, and we've applied the coin. We actually get the exact same state as what we had up here. I can also send these notes to Chris or Harmony or Gabriel or someone, and they can.
Yeah, send them to me.
Okay, I'll send them to Chris, so you guys don't have to worry about that, because I'm doing something you shouldn't do if students are taking notes, which is copy and paste, because students can't do that. They have to rewrite it. But hopefully in this format, it won't be too much of a sin. Okay, so basically nothing happens with the coin in this step. Again, later on, evolution will be more interesting. And finally, we have the shift, which is typically the flip-flop shift. And what happens is, if we go back up to our picture here, so you have 0 pointing to 1. What this amplitude will do is it will jump to 1 and it will point back to 0. And likewise, if you're at 1 pointing to 0, so if you're this arrow, you'll jump to 0 and then you'll flip-flop back so that you point back to 1. So basically what happens is that these arcs end up swapping. And then if you're at 0 pointing to itself, nothing happens because you're actually hopping or walking now. And if you're pointing to yourself, you would just stay there. So what would happen is the following. And I'm actually just going to draw it out. I'm drawing it bigger so I can label all of these amplitudes. Maybe I drew it a little too big because I have to scroll. Okay, so this amplitude here on this self loop, it stays the same. This is still minus 1 over the square root of 20. these two amplitudes are now going to flip-flop. So before this is minus 1 over root 20, and this is positive 1 over root 20. So this is going to hop and turn around. This will hop and turn around. So this becomes positive 1 over root 20. This becomes minus 1 over root 20. And the same thing happens with all of these pairs here. So this becomes positive 1 over root 20. This becomes minus 1 over root 20. And this is positive 1 over root 20. And this is negative 1 over root 20. And then here, this was positive 1 over root 20. That's not going to change, as were all of these amplitudes. And this amplitude. And then all of these pairs, well, these are all positive 1 over root 20. So when these swap, nothing's going to happen. So these remain positive 1 over root 20. And that pair. And this pair as well. All right, so this is one complete step of our algorithm, and we're going to apply this many times. And you can see that this is now different from what we started with. So our initial state, everything was positive 1 over root 20. And now what we've done is, at this marked vertex, it has one amplitude at the self loop that's negative 1 over root 20, and the rest are positive. Whereas here you have, you also have one negative and the rest positive, but the negative is not in the self loop. It's in this edge pointing to the marked vertex. This is the marked vertex. And the idea is that if we keep on applying this, we're actually going to get some interesting behavior. And the idea is that the probability is actually going to accumulate at this marked vertex over time. And so to demonstrate this, I'm not going to write all this out, step after step after step like this. We're actually going to simulate this in Python. And so here is a Jupyter notebook, which is just an interactive interface for Python. I don't know how well you guys can see that. Maybe if I zoom in. All right. Let me make sure I can see the chat window. Okay, I pulled up the chat window there. Okay, so I'm not sure how familiar you guys are with Python, but we're gonna program it. Okay, so first thing I want to do is I want to import some modules. And actually for now, the only one I need to import is just NumPy, which is a numerical Python library. And I'm going to import that as NP. So you'll see me later if I'm calling in one of these functions from NumPy, like a square root, I'll write np.square root. So I'll be calling the NumPy function that's a part of, sorry, I'll be calling the square root function that's a part of NumPy. Let's set some parameters. So let's say the number of vertices is 4, and we can tune this later to make it bigger. So for now, we'll make that the only parameter. And now we're going to define our initial state. Okay, so what I'm going to do for this for the state of my system, and I'll call this psi, is I'm actually going to write this as a 2-dimensional array. Because if you look back at the way I was writing it as what vertex you're at and then which vertex you're pointing at. So this is vertex 0 pointing to vertex 0. This is vertex 0 pointing to vertex 1 and so forth. So I'm going to do the same thing. I'm just going to write my state as a 2-dimensional array. So the indices specify which vertex you're at and which vertex you're pointing to. And so I'm going to start off with an array of all zeros, and then I'll fill in the values. So it's going to be an n by n array because if there's because there's 4 vertices, right? And then there's 4 vertices you can point at. And I'm gonna go ahead and fill in the values. So or I guess like, well, yeah, I'll do it iteratively. There's better ways to do this, but this might be the most clear. So I'm gonna iterate I from 0 to n minus 1. And then I'm going to iterate j, again, from 0 to n minus 1. And I'm going to say psi of I pointing to j is equal to 1 divided by the square root of 20, which in this case is, oh, did I say 20? Oh, this whole time I'm using the wrong number. No one said anything. There's actually 16, right? Yeah, there's 4 times. Oh, this is 6 square root of 16. Well, now, well, that's silly. That's what I get for not writing this out beforehand. But that's one of the things with programming, right? It makes you catch your mistakes because the program is not gonna.
Square root of 16 is 4, of course.
Yeah, I'll write the square root of 16 though, just so that, because it's basically n times n. Well, and also later when we add more self loops, it's gonna be different. So let me correct this real quick, especially since I'm gonna be sending Chris the notes. I don't want this to be forever wrong. Oh man. These should be square root of 16, not the square root of 20. Maybe I'll fix it later. Okay. I'm not gonna make you guys watch me do all that. So this should be square root of n times n, which is just n, but later on we're gonna add more self loops, so I'll just leave it like that. Let's go ahead and print this initial state. First, before we proceed. So that is one quarter. Okay, so basically 0 pointing to 0 has an amplitude of a quarter, 0 pointing to 1 has an amplitude of a quarter, and so forth. So everything starts off with amplitude of a quarter, or 1 over the square root of 16, as we expect. Let's specify the initial state. Not the initial state, the marked vertex, sorry. And without loss of generality, we'll just make that vertex 0. Basically, if we change the marked vertex, it shouldn't change the evolution at all because the graph is vertex transitive. All right, so first thing we want to do is apply the oracle. So we want to query the oracle. And so what we want to do is at vertex A, we want to negate all of its amplitudes. So I'm going to say for I is in range of n, I'm going to take psi of A I and multiply it by -1. So basically vertex A point, so I is going to go from 0 to 3 in this case. So basically this is the amplitude of the marked vertex pointing to 0, the marked vertex pointing to 1 and 2 and 3. These are all going to get multiplied by -1. And so if we print that, we see that we got this here. So 0 pointing to 0, 0 pointing to 1, 0 pointing to 2, and 0 pointing to 3. These have all become negative, and the rest of them are unchanged. Now we want to apply the Grover coin, which inverts each amplitude about the average. So we want to go through each vertex about each amplitude about the average amplitude at that vertex. So we're gonna go through all the vertices. So I is gonna go from 0 to 3 through all of our vertices, and we want to calculate the average at this amplitude at this vertex. So calculate the average amplitude at this vertex. So we'll put this in a variable called average, and we're just going to sum up all the amplitudes first, and then we'll divide it by 4. So for j in range n, we're going to add this to our average. So we're going to add this amplitude at vertex I pointing to vertex j to our average, and then the average we can obtain by dividing it by the number of vertices. Now that we have the average, we can invert each amplitude about this average. And so now I'm going to need to create some variable to store this, because if I store it in psi, I'm going to overwrite values that I might need. So let's say temp is just all zeros for now. Okay. So the way that you invert, and maybe I should show this actually. So let's say, let's go back to the coin. So here's our number line. Let's say the average value is here, and your amplitude is currently over here. Okay, so the idea is we want to figure out what this should be, what value we should reflect to. So basically this difference here is mu minus alpha. And so what we want to do is you want to end up mu minus alpha in front of mu. So we want this to be the same distance. So this is going to be mu plus mu minus alpha, which is 2 mu minus alpha. So that's if you want to invert that way. If you want to invert the other way, let's see what we get. So this is mu. Let's say the amplitude starts off over here now, and you want to reflect over there. So this distance is alpha minus mu. So we want this distance to also be alpha minus mu. So this value is going to be mu minus alpha minus mu. So this is mu minus alpha minus mu, which becomes, again, 2 mu minus alpha. So basically, if we want to invert, we just take each amplitude and we turn it into 2 times the average minus whatever the amplitude was. So to invert, we go from the amplitude to 2 times the average minus the amplitude. So if I do that here, I'm going to turn this. This is going to be 2 times the average that we just calculated minus the amplitude. And that should do it. So let's go ahead and print this state that I'm putting in this temporary variable temp. Oh, I'm missing something. Oh, wait, I need to go through each amplitude for J in range. Here we go. All right, so we see nothing happens, which is what we expected, because before, after the query, all of these amplitudes are the same. So if we invert them about their average, nothing happens. All of these are the same. So if we invert them about their average, nothing happens, and so forth. So we see that nothing happened as expected. And now the final thing we're going to apply is the flip-flop shift. And so to do that, all we need to do is take the state of I pointing to J and reverse it. So that becomes a state of J pointing to I. So I'm just going to go through all of the possible amplitudes, and I'll say that psi of ij is equal to this temporary variable, which is the state after the coin, of ji. And now if I print this, this is exactly what we expect. So basically, 0 pointing to 0 is negative a quarter, pointing to all the other vertices is positive a quarter. At vertex 1, pointing to 0 is negative and everything else is positive. And so for all these, pointing to 0 is negative. So if we look at this picture and replace this 20 with 16, or you make these 1 quarter. So we have negative a quarter and then positive, positive, positive a quarter. That's that first row of this. And in the second row, we have negative, positive, positive, positive. And then again, we have negative, positive, 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 and so forth. So everything matches here. All right, so the reason why we coded this isn't just so that we could do this once, but so we could apply it many times and see what happens and not have to like recalculate and redraw everything by hand. So what I'm going to do now is I am going to run these steps. So the Oracle query, the Grover coin, and then the flip-flop shift, I can run it now multiple times. So let's set the number of steps. So let's say we want to take 10 steps. So what I'm going to do now is I'm going to combine all these. I'm going to say for t in range of the number of steps, I want to do all of these. So I want to query the Oracle. I want to apply the Grover coin. I have to indent all these. And then I want to apply the flip-flop shift. And if I run this, oops. Oh, I didn't run this cell. Okay, I ran that cell. Now steps should be defined. All right. So basically, after 10 steps, Well, first of all, if we have the state here at a bunch of places, this looks a little messy. So let's clean this up a bit. So let's not print everything. And in fact, let's just, oh, I'll start with this. Okay, so basically this is the state after one step of all three operations. This is the state after two steps, after three steps. So if you look here, actually all of the amplitude is actually at the marked vertex. So the amplitude of 0 pointing to itself is -0.5, 0 pointing to 1, and 0 pointing to 2, and 0 pointing to 3 are all 0.5. There's no amplitude anywhere else. And so, and actually here, the amplitude is all in that self loop at the marked vertex. So of course, what we care about when we measure quantum walk is the probability of finding the particle at a certain vertex. So let's actually calculate that. So let's print, instead of the entire state, let's print the probability at the marked vertex. So what we can do is we can print. So basically, we want to take this first column, this first row here, because these are all the amplitudes at A. So I want to take psi of A, and I want all of the remaining amplitudes. So to do that, I'm going to do this. So basically, this gives me row A, and I'm keeping all the columns. Now what I want to do to get the probability is I want to take the square of them. So I'm going to use the square function in NumPy, and that will square every entry element wise. And then I want to add up all of these. So I'll do np.sum to sum up all of these. All right. Let's also print what time step we're at. So let's see. So this is after one step, t starts at 0. So I'm going to print t plus 1. So after step 1. Let's put a tab too to make it a little nicer. And let's print the probability of the initial state too, before we apply any operations. So this would be at 0. Run all the cells. Here we go. Okay. So what we see is that initially the probability, if you measure the position of the walker with probability a quarter, you'll find it at the marked vertex, which makes sense because if we start in a uniform superposition, then we have, and there's 4 vertices, then we should have a probability of a quarter at every vertex. After one step of this quantum walk search algorithm, the probability is still a quarter. Then it becomes 1, and then 1, and then a quarter, 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 and so forth. All right, so basically we see that the probability reaches 1 after just 2 steps. So after 2 steps of this, you can measure the position of your quantum walk, and with certainty, you will find that the walker is at the marked vertex, and so you're guaranteed to find it. If your graph is bigger, so say we have a graph with 32 vertices, then it might take more time in order for that probability to build up. So let me run all the cells in this notebook. You can see the probability now starts much smaller. This starts at 1/32, which is 32 vertices. And the probability builds up to roughly 1 after 8 or 9 steps. And then it goes back down. And then it builds up again to almost 1 at about 26 or 27 steps, and so forth. So maybe we'll plot this. So I want to save all these probabilities. So let's see. I would save it in an array. So create an array to store the probabilities. So I'll call this prob is equal to numpy zeros. And I guess I need enough. So the size of it should be the number of steps plus 1 so that I can store the initial probability as well. So this thing here is my probability at time 0. So I'll store it there, and then I'll print that. And then down here, this is the probability at time t plus 1. and then I want to print that. And then now I can, let's see. Oh, let's run this, run all. Oh, steps, not step. Steps. So run all. Okay, so now I can plot these. So I need a plotting library. Let's do that. So let's import matplotlib as plot. Run that. And now what I'll do is I'll plot these. So plot the probability. Oh. Import, let me run everything first. Run all. Oh, ha. No, I did. .pyplot. There we go. Run all. Here we go. So here we see the success probability starts at 1/32. It goes up, reaches 1, and then it's periodic. It goes up and down like that. So we want to measure the position of the particle here when the probability is high. That will find the marked vertex. I want to say, like, are there any questions so far? Because I'm so used to teaching my undergrads. If you do have questions, feel free to actually jump in. I don't. As a physicist, I don't mind questions throughout. And we can make this bigger. 100 steps. Run all. Maybe I should turn off this printing thing. All right, so we see a similar pattern, right, where it starts at, in this case, 1/256 as a probability, and then it reaches 1 at whatever this time is, 25-ish steps, and so forth. All right, so hopefully this is stuff that you've seen before from Harmony going over it. So this result of searching the complete graph with a self loop at each vertex. So this was first in a paper by Mbinus, Tempa, and Ravache, which was written back in like 04 or 05, depending on if you look at when they wrote it or when it was published, something like that, 04 or 05. And so, yeah, so I didn't read this paper until like a decade after they wrote it. But when I read it, and I saw what they did, my thought was like, how come they put a self loop at every vertex? Like, what would happen if you had no self loops? Or what would happen if you had more than one self loop, like 2 self loops or 3 self loops or 4 self loops? And so that's going to be what I want to talk about. So what happens if you have no self loops? Or what happens if you have multiple self loops per vertex? Okay. So yeah, we're gonna simulate these and see. And I wrote a paper about this where I prove everything. So if you're interested, I can point you to that. But we'll just simulate it to get an idea together what happens. This thing where you have multiple self loops, this in some sense is a type of lazy quantum walk, because as you add more self loops, then there's more probability of the walker staying put by walking to itself instead of hopping to another vertex. And so this, in some sense, is a type of lazy quantum walk. Unfortunately, the term lazy quantum walk was already taken, so I had to pick a synonym. So I just looked up, synonyms for lazy, and I picked lackadaisical quantum walk. So when I talk about a lackadaisical quantum walk, it's just a quantum walk on a graph where you put multiple self loops, and if you put more self loops, it's more lazy or more lackadaisical, and put fewer self loops, it's less lazy. So you can tune them out of laziness. in this sense. So that's where this comes from. And so let's go ahead and see what happens. So first, let's see what happens when there's no self loops at all. So when there's no, well, let's turn off all this printing stuff too. Let's pick a smaller graph. 64, that should be faster. 40 steps. I'll comment that out. Let's make sure this works. Okay. I guess I can do a little bit more time. 60 steps. So you can see that's periodic. All right, so this is with a self loop, what you saw with Harmony. Now let's modify this so that we have no self loops. So now what's going to happen is instead of there being 16, not 20, 16 of these amplitudes, we're not going to have these self loops. So now there's going to be 12 because there's 4 vertices and each one has 3 different ways that it can point. So there's now 12 amplitudes, and there's no amplitude of pointing to yourself because there's no self loop anymore. So how this initial state is going to change, actually, let me save this so that way you guys have, so this is one loop. And then let's make another one. No loops. Oh, great. Okay. So now we're going to program this without any loops at all. So the idea here is that for the initial state, if I is equal to j, we want psi of I, j to be 0 because there's no amplitude of pointing to yourself. And otherwise, we do have an amplitude, and it's going to be 1 over the square root of n times n minus 1. So this is why I didn't just do 1 over n earlier to make this a little bit, I don't know how much easier it is to change, but you know. So here's the initial amplitude, and we see again, the amplitude on the diagonal should be 0 because that corresponds to pointing towards yourself. And we do have amplitudes on the off diagonal. What else should change? Well, now for the Grover coin, this should change. So when we calculate the average, we don't want to divide by n. We want to divide by n minus 1 because that's how many amplitudes there are at each vertex, how many different ways you can point. And when we invert each amplitude, we don't want to invert the 0 amplitude. We only want to invert the ones that are not pointing to yourself. So I'll say if I is not equal to j, then we want to do this. And if I is equal to j, it will just stay 0. And then this shouldn't matter because if the amplitude of pointing to yourself is 0, then this just makes it stay 0. So that shouldn't change anything. Okay, let's see if it run all. All right, so we see that the probability, it starts at, what did I use, 64? So it starts at 1/64th, and the probability builds up, and it doesn't reach 1, it actually reaches roughly a half. So let's change the scale of this. So plot dot the y-axis, let's set the limits to be from 0 to 1. So you can see it doesn't reach 1, it only reaches a half. So if you have no self loops, what happens is that the probability reaches a half, whereas before it reached 1. So let's say C simulation. So we had one self loop, the probability reaches 1 basically. And now the probability only reaches a half. So it seems like having one self loop actually is better than having no self loops because the probability reaches 1 instead of a half. Any questions about that before we go to multiple self loops? All right, I don't see anything in the chat, so let's keep going. Let's save this. And let's save a copy. Let's save this as multiple loops. All right. So now we're going to need a bigger state. So what I'm going to do is, again, if we have 4 vertices, I'm going to make, so 0, 0 would still be pointing to itself. 0, 1 is pointing to the neighbor, 0, 2 is pointing to another neighbor, 0, 3 is pointing to another neighbor. Let's say I have more loops. What I'm going to do is I'll let 0, 4 also be a loop. So this is a loop, this is a loop, 0, 5 is also a loop. So in this case, vertex 0 has 3 loops and so forth. So this is how I'm going to, in my program, store all the information. So there's actually no vertex 4 or 5 because the vertex is only 0 to 3, but I need space to store these amplitudes. So I'm going to store it like that. And the same idea with like, vertex 1 pointing to 0, vertex 1 pointing to itself, that's a loop. Vertex 1 pointing to 2 is a normal edge, 1 to 3 is normal, 1 to 4 is a loop, and 1 to 5 is a loop. So this is if we have 3 loops per vertex and so forth. So what I need here is I need more space. So I need to specify the number of loops. So let's say the number of loops, let's just do 3. There's 3 loops. So I'm going to need this to be, let's see, n plus the number of loops minus 1. Right? So if there's 4 and 3, that would be 7 minus 1 and 6. 1, 2, 3, 4, 5, 6. Okay, good. That makes sense. And now the initial state, well, I'm going to iterate through all possible directions. And now they're all going to have the same initial amplitude. This is going to be 1 over the square root of n times n plus the number of loops minus 1. Let's run this. Loops is not, oh, I need to run this. I'll run that first. Run this. All right, so we see that the initial amplitude is all the same everywhere, which it should be. So this is, yeah, so at the marked vertex, we want all the directions to be negated. So I'm going to sum over all the possible directions at the marked vertex. This now needs to be bigger to store everything. Now for the average, we have more directions that we can point. And then we divide by the total number to find the average. Now we invert each one about the average. So again, we want to go through all the different directions. And we have a self loop now, so we can drop that. So we're inverting all of them. And then for this flip-flop shift, oh. So this part's gonna be a little different. So here, when we're flopping these, so the amplitude at 0, 1 and amplitude at 1, 0, these are gonna swap. But I can't be like the amplitude at 0, 4 swapped with the amplitude at 4, 0. There is no 4, 0 because there's no vertex 4. So the amplitude at 0, 4 has to stay the same, and at 0, 5. So basically, if the direction is greater than the number of vertices, or greater than or equal to the number of vertices, then those amplitudes should actually stay put. So for j in range n to n plus loops minus 1, I'm not gonna swap those. So basically these directions now are like 4 and 5. Yeah, so 4 and 5. So let's go through, let's run that and plot it. What's it printing? Do I have a print statement somewhere? Oh, that might be from that. Fine. All right, so what we see now is if we have 3 self loops, it's not as good as 1 self loop. So 1 self loop reaches a probability of 1. With 3, it reaches, I don't know, a little under 0.8. What if we give it, let's give it in between. Let's say it's 2 self loops. Run all. So again, it's not as good as 1, but it's better than 3. Let's say we have 4 loops. Let's run all. Oh, it gets worse still. If we have 5 loops, run all, it gets worse still. And so actually, it keeps on doing this. So if we keep on adding more loops, let's say 10 now, it actually gets worse and worse and worse. You see here now, it's not even reaching a half. So what we see here for the lackadaisical quantum walk, when you have multiple self loops, is that, well, I guess we can summarize everything, right? When you have no loops, the probability is a half. When you have one loop per vertex, the probability is 1. When you have 2 loops, the probability was, oh, let me actually estimate it. Maybe I should have been doing this as I went. What is that? About 0.9, something like that. 3 loops. Let's just do another one of these. And then this will be the end. Is it a little less now? Maybe 0.75, I don't know. Something like that. And it basically keeps getting worse. So what we see here is that there's actually an optimal amount of laziness. Because remember, as you add more loops, it's getting more lazy because it's more likely to stay put. But it looks like being a little bit lazy is actually helpful compared to not being lazy at all. And so, so maybe this is a life lesson. There's an optimal amount of laziness. I don't know, but this is a pretty interesting thing that there's some optimal amount of laziness for searching these graphs. And so, so yeah, so this is what the main point I wanted to express in terms of further research on this. Another thing that I explored in a subsequent paper was if you have, instead of having an integer number of loops, like 3 loops, what happens if you replace them with a single weighted loop that's weight L? And so now L can be a real number, a positive real number, as opposed to here, it had to be a positive integer. And so this allows you to generalize it, and you actually get the same behavior where one loop is the best, but now you can smoothly transition between these different values. So you can have like 1.5 loops or a weight as 1.5 and so forth. So this is follow-up work. And then there's also been work looking at other graphs. And so, yeah, so these lackadaisical quantum walks, they're a type of lazy quantum walk. And it seems like also with other graphs, there's also some optimal amount of laziness. That making it a little bit lazy is actually better than not being lazy at all. But if you're too lazy, then it becomes too slow. And so that's the moral of the story. Thank you for listening. Are there any?
Thanks, Tom.
Yeah, you're welcome. Are there any questions?
Yeah, questions.
I have one question. So you have 2 models. One is to augment the state space by adding a bunch of integer loops, and the other is to adding weights. So if this weight is integer, are they equivalent in some
Yes,
way?
they
or
are. Yeah,
oh,
so
they
if
are.
L is equal to 3, it's equivalent to this with 3 loops.
Ah, I see.
Yeah.
And does this work in general, not just the complete graph?
Yes, it works in general.
Yes.
Yeah, so the way that I specified how to take care of these weighted loops, it makes it so that it's equivalent to this when L is an integer.
Okay.
So the amplitude on 2 loops on the same vertex will be equal. Is that?
Yes.
Yeah, unless you do something silly with the initial state or something. But
yeah, exactly. Yeah, because I start in a uniform state, the amplitudes of all of these are equal, and that's how you end up converting to this. Yeah, I can point you to a paper, or we can talk about it, offline.
Sure.
We have time after this if you have time, but that's not. Yeah, I think we understand. More questions?
What other graphs have you looked at?
There's a lot of graphs now. So in terms of the ones that I've looked at the complete bipartite graph, a 2D torus. I've looked at strongly regular graphs. I've looked at the hypercube. And I think there's some others. But basically, we notice a trend, and then there's some researchers who were able to prove this in general, that the optimal amount of laziness, so what L should be, L should actually be the degree of the graph divided by the number of vertices. So basically, if you have a vertex transitive graph, this always holds. So researchers have looked at vertex transitive graphs. Yeah, and also I've also looked at the bipartite graph, which is not regular, so it would be not vertex transitive. And it turns out when the graph is not vertex transitive, it's a lot more messy, and we don't have a clear statement like this, like we do for vertex transitive graphs. Also, if you have multiple marked vertices, it gets a lot more messy too. Oh, people have looked at not just the torus and 2D, but like 3D lattices and higher order lattices, one-dimensional lines that are periodic cycles, cycles, and so forth. Yeah, and I can point you guys to all of these things if you're interested.
Yeah, Tom, if you could just add a few citations to when you
I can do that.
Send me the slides. If you could just add a few citations.
Yeah, I'm happy to do that too.
Could we get the notebook?
Yeah, I can send you this as a PDF.
Yeah, but the actual note, no, the Jupyter notebook.
Oh yeah, I'll send you the code. So I was saving them all as different files that way.
Yeah.
You'll have them all as separate files as well.
I'll put them on the web page so people can find it.
Yeah.
Thank you, Tom.
Yeah, you're welcome. Thank you again for having me.
This is just curiosity. So you're using Python. Do you have any preferences versus Python versus Sage?
I haven't used Sage. I know that a lot of people in your group use it and like it. I just happen to have already known Python before, and so it's just not wanting to learn something new.
It's very similar.
I tend to use actually Mathematica a lot in my research. But for a presentation like this, I thought Python was more appropriate because not everyone has access to Mathematica, whereas Python is open source as a Sage.
Yeah, I mean, I don't know. For example, your flip-flop operation would just be a transpose.
Yeah.
And
I think that there are more advanced ways to program it in Python.
Well, that's not the issue. That's not an issue. But for our point of view, the reason we use Sage is because if we start constructing weird graphs, it's a lot easier to do that in Sage than in raw Python.
I'm sure.
Yeah, so that's where but otherwise the calculations we would be doing would be very similar to what you're doing.
Yeah, on more complicated graphs, I tend to use Mathematica because that's what I learned as a physicist. Most physicists know Mathematica.
Yeah. More questions?
Oh, I have a question. So Tom, do you have any physical intuition for why having the loop would help, and the more loops you have, the worse you will guess? Why? Do you have any intuitions?
So why does having a self loop help?
Yes.
So you can actually, if you actually calculate, or actually in the simulations, if you print where all of the amplitudes are, what you find is that when you have one loop and the success probability reaches 1, the probability is entirely inside of the self loop. So basically, when you have that self loop, it gives you another place to store amplitudes that you wouldn't have if you had no self loops. So that's like some intuition. So basically, because we can see it evolve and we can actually calculate it for the complete graph. Basically, since the final state is just only the self loop, then it's not possible to have that state if you don't have any self loops. So to take advantage of that, you need a self loop at least. Another reason for the intuition is because if you don't have a self loop, then your final state where you have probability of half, it's actually split up so that half the probability. So again, if there's no self loops, half the probability is 0 pointing to the other vertices, and the other half is actually at the other vertices pointing back to 0. So these other amplitudes that are, the unmarked vertices pointing to each other, these basically have zero amplitude. So the only amplitude is marked pointing to unmarked and unmarked pointing directly to marked. And so I actually have a paper as well where I explored that, because basically if you identify that the other half of your probability is at the unmarked vertices pointing to the marked vertex, then if you measure the position of the particle and it's not at the marked vertex, so let's say you get at vertex 1, you're like, oh no, it's not the marked vertex. But then you go, oh wait, but if I measure which direction it points, that tells me where the marked vertex is. And so you found the marked vertex already. So if you give yourself that additional measurement of the internal state of like what direction it points, you can actually still have a probability of 1. But that would be an additional, resource that you'd have that people don't typically take when they look at a random walk. They only look at the position of the particle.
Okay, thank you.
Yeah, you're welcome.
Of course, you've got to be a bit careful with intuition in this context. So the example I think of is just the continuous walk on a complete graph.
Mm-hmm.
On a large complete graph, basically the walker stays at home.
Mm-hmm. Yeah.
And that seems to even surprise physicists when I point it out to them. But I think Feynman once said the nice thing about intuition is you can always retrain it in light of the facts. But I've never been able to find the actual quote.
Yeah, all the time. Like when physicists take modern physics and like learn about Einstein's theory of relativity, we basically have to relearn intuition.
Yeah.
Or when we learn like anything quantum, we have to relearn intuition. It's like, what do you mean a particle can tunnel through a potential barrier? So, yeah.
Any more questions?
Feynman would say that.
Sorry. Yeah.
Oh, go ahead. Yeah.
Any more questions? Okay, I'm going to stop the recording.